Okay, got a nice fresh battery and unloaded the memory card, so I'm good to go for another section of tracing and desoldering. So, where did I leave off? I want to trace out this 138 and find out where all he connects to see if I can get rid of him. Plus I want to finish tracing out the multi-sign connector and see what all is hooked up to him. So that's my next set of goals while I sit here and wait for my pizza. And here we have yet another one of my little cameras hooked to the battery, charging it for next time. Uh, 74. Is that 130? There he is. So pins 1, 2, and 4 are the inputs, or 1, 2, 3 are the inputs, 4, 5, and 6 are the gate drives. So 1, 2, and 3 right here are the 3 to 8 decoder inputs. So 3 bits binary here, which can be 0 through 7, will decode to outputs 0 through 7, probably on this side of the chip. So I'm just going to quick chase them backish, across-ish, the card-ish. And they come back over to this chip right here, which is one of the RAMs. That's intriguing. So this must be the address bus on the RAM. So let's make sure I have the right set of pins here. Oh, maybe not. Yep. So this is either the data or address bus off the RAM that's getting decoded. Now, 5, 6, and 7 are also, they're not address pins, but they're gate pins. So if they're not in a happy state, it will not allow the chip to decode. So these two inputs are tied high, low, which is probably the good state, and this pin here is actually wired off to somewhere else. Where exactly? Not sure yet. So it comes over to those two bumps. Right there. So that gets me to there. Which gets me to there. At some point, I'm pretty sure this is going to trace back to a 138. So this 3 to 8 decoder is chained off of this 3 to 8 decoder, which is just slightly confusing, but not unexpected. Now let's make sure. Just checking out where all these are hooked to. was tied high. Okay, so I chased that through, and I know where all the set resets hook into this guy. So that one was right there. Next one over is right there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Up through pin 13 is all taken care of. So it just leaves me those last 3 bits. So looking at the pin out of these chips, 16, 15, 14, 13, 12, 11, 10, 9, 7. So 7. 1, 2, 3, 4, 5, 6, 7. So let's see if 7 goes anywhere. Oh, yep, 7 does. I went back to the same chip. But 14 and 15 also go somewhere. Ooh, and that one looks like they go into multiple somewheres because there's this little, I don't know, woofty, I guess you'd call it. So let's see where these run off to. One in from the top. Goes to there. All the way back to there. And goes up into the mezzanine card, which I had stuck back over here for safekeeping. So this plugged in like that, so it's coming in this drip header here. So this pin over here comes in pin 2, 1, 2, which is used for absolutely nothing on this card. Another way to, if you get confused as to where stuff go on double-sided cards like this, you can hold them up to a light like this and you can see the shadows of the traces on the other side. So he plugged in like this. Pin 2 came into this card and did absolutely nothing. So pin 2 I think we can check off as unused. Now just to make sure, follow it back through here, yeah, and it goes exactly where we thought it went. Now it could, this is a very big could, have branched out underneath one of these chips, but kind of unlikely. I mean, it sort of, yeah, about the only place would be underneath this guy, and that's another 138, so it'd make absolutely no sense for this 38 to drive that 38. But just in case. Oh, he's good. Alright, so that pin doesn't go anywhere. And that's the reason why I'm checking out each one of these driver chips individually versus just assuming it went to something over here. Because, you know, if they had some gate over here where they needed one more drive or enable signal, and they had a way to get it across the card, they will wire it all the way across the card just to save the cost of the gate of putting another TTL package on the card. This pin splits right here and goes on either side of this trace, which is a little weird. 1, 2, 3, 4, and 5. And then splits off right here. And goes to this guy. Yes, indeedy. So what is that guy? That's a 125. So it latches this gate, or enables it, don't know which. And also goes to 1, 2, 3. 1, 2, 3, goes to here. Oh, here's another 125. So it's enabled to these two 125s. So, of this chip, this pin right here may still be in use and may be needed. So, I can't get rid of it yet, unfortunately. Now, as I trace out the rest of the circuit, I might find out, oh yeah, that goes to something I can ignore, and I will do so. Now, one of the chips I had enabled to was this guy, whose one of his inputs was the touch sensor I got rid of. So, there's a good chance that might be sort of like a glue logic chip, and I may need that enabled. So anyways, back to this little strip connector here. Pin 1, 2, 6, 7, 9, and 10. Well, that's ground. Or on the back side. So it looks like 1, 2, and 3 are not connected to anything. Now, pin 1 was the key. Yeah, pin 1, 2, and 3. Pin 3, there was no pin, so that doesn't surprise me, it's not connected. Pin 1 being not connected is a little bit of a surprise. And I want to make sure it's just not... Nope, he's disconnected. So let's go start with pin 4. 4 goes over to a 750 ohm resistor, which then looks to go absolutely nowhere. It goes to ground. Just double checking to make sure I didn't miss something. Nope, it just goes to ground. So maybe that's some sort of far end selector enable line? Don't know. Pin 5 comes out and goes up to a 75117, which that is a differential line driver, I do believe. Okay, 5 goes to 5. 57. There he is, 55. What's RS? Data in, data enable. Oh, receiver. So that's the send receive bit. So what this chip does is it takes a single-ended circuit and makes it differential. Now, single-ended, if this is V and T, so this is time and this is voltage. A single-ended signal for 1 to 0 would have waveform like that, and the chips on either end would have thresholds where if it's above this dotted line here, it's counted as a 1. If it's below this line, it's counted as a 0. And the stuff in between is sort of the indeterminate state. It's not high enough to be a 1, but it's not low enough to be a 0. And depending on the quality of the chips, that band will either be smaller or bigger based on the inputs. Well, one of the problems with single-ended inputs over long stretches is the wire acts as an antenna and starts picking up electrical spikes and just general noise. Now, if you have a spike that just happens to go either into this into this indeterminate state, or even worse, all the way bounces the line all the way down into the opposite polarity, then you get errors on your bus. So what differential does is you have two wires. I'm going to draw the slope exaggerated with a waveform that sort of looks like this. And then your second pair is 90 degrees out of phase, or inverted, with compared to the first wire. Now, again, there is a band down the center, which is your indeterminate state, but when just randomly label these A and B, when A minus B is positive, it's a 1, let's say. A minus B is negative, it's a 0. So A is greater than B here, so it'd be a 1. B is greater than A here, so this would be a 0, and a 1, and a 0, and so on and so forth. Now, since these two wires are running parallel to each other to the whole distance of the bus, if you pick up a noise spike, you're probably going to pick up an equivalent noise spike on the second pair, of the second leg of the differential pair. So that even though you got this massive noise spike in the middle of your signal, since both sides got the same noise spike, A never went below B, and therefore you still had a red a 0. So this is a very good, differential pairs is a very good way to reject what they call common mode noise. Common mode being the noise appears in both the A side and the B side of the signal. If you look at op amps and comparators, there's usually a parameter in there about common mode rejection, and this is the sort of stuff that it's talking about. But in the case of this serial bus, this is a method to keep long tracks of wire that go around lighting ballasts or motors, or just bad running or bad placement in general, from coupling that noise into the system and causing errors on the link. So one example of where they might want this is if they had these placed around an airport, let's say, by each gate. Well, you have hundreds of feet between each one of these signs, so they'd use a differential signal to try and reduce the amount of noise it picks up, and it extends the length that you can use the same bus without redriving it. So that's my mini tutorial on differential pairs, or differential drivers.